Okay, so we're going to go through and do one of the two examples I talked about in class that we wouldn't have time to get to. So the first example here is calculating a line integral. So you can see here we have a ray going from point A, which is 1, 0, 0, to point B, which is 1, 1, 1. And we have a vector field here. F is equal to x squared ax minus xzay minus y squared az. We want to calculate the line integral along the path L, where L is defined by the line segment AB. So you can see here, this presents an issue. We have that both the y-coordinate and the z-coordinate are changing together. So if we go to our differential length vector, which is equal to dx ax plus dy ay plus dz az, and we calculate the dot product of f dotted with dl, which is going to be a multiplication between the x component. So we would have x squared dx, the y component with the y component here, xz dy, and the z component with the z component here, y squared dz. You'll see that we're not going to be able to calculate the integral directly because we have changes in more than one direction at one time, and it's a simultaneous change as we go along this path here. So what we have to do is we have to parameterize this equation. So there's a couple different ways we can do this. One way is that we can notice that x isn't changing. At point A, x is equal to 1. At point B, x is equal to 1. And all along this segment, x is always equal to 1. So that means that x is constant, it's equal to 1, and that the change in x is equal to 0. Okay? So that's very helpful, which means this term right here is going to drop off. But then you'll see that we have both y and z changing at the same time, and that still presents an issue. But we can notice something here. If we only have y and z changing at the same time, we can come up with an equation that defines y in terms of z. So you can see that this line right here is just a linear line segment, right? So we can use point slope formula to find that. But it's very easy to notice that if we just go from 0 to 1, it's an increase in y and an increase in z at the same time. So from there we can notice that no matter where we're at, that y is going to be equal to z, right? Here, y is equal to 0, z is equal to 0. We move along the path, y is equal to 1, z is equal to 1. So this right here is a parameterization, right? So then we can take the derivative of y with respect to z. So dy dz is just going to be equal to 1 because the derivative of a first order term is a constant. And then solving this equation, we can say that dy is simply equal to dz. Okay? So now what we can do is, saying that dx equals to 0, we can substitute in y is equal to z and dy is equal to dz, and we can have this f dot dl all in terms of either dy or dz. So, putting in dx is equal to 0, and putting in y is equal to z and dy is equal to dz, instead of having xz, we're going to have xy, because I'm going to change all the y's to z's, all the dz's into dy's. So we have negative x, and then replacing z with y, and then dy. Okay? And over here we have minus y squared, but we have here dz, we're going to replace that with dy, and we can do that because dy equals dz. And then we can also make use of the fact that x is equal to 1. So we can simplify this a little further. So we have minus y dy, minus y squared dy, and then we can factor out the dy, and we simply have minus y squared dy. Okay? So now we have the whole equation and we only have a change in one dimension, right? So it's very easy to calculate. So now we'll notice that the change goes from y equals 0 to y equals 1. Okay, that's going to be our integral bounds. And I'm going to come over here and do the integral. So we'll say y goes from 0 to 1. F dot dl is right here. So we're going to have minus y squared, and integrate with respect to y. So the integral of a first order term is going to be 1/2 y squared. The integral of a second order term is going to be 1/3 y cubed. Our integral bounds are going to be y equals 0, and we're going to go to y equals 1. So it's fairly obvious that when we evaluate at y equals 0, these terms are going to be equal to 0. But when we evaluate at y equals 1, right here we're simply going to have 1/2, and right here we're simply going to have 1/3. Okay, so then getting a common denominator, we could say that this is minus 3/6 minus 2/6, and our answer then is equal to minus 5/6. Okay.